the cornea. So Jagger, it's measuring from black to black through the center. That's 11.2 millimeters. And he will then choose to enter the spectacle prescription. So Jagger, what are we going to go for?
There you go for a -5 with a -1.25 cylinder at 180.
Okay.
Click done. And the software will produce a design for us to review based on this corneal topography. If it decides to play ball today, obviously my computer is very, very fast.
Exceptionally fast.
Yeah. So, Charlotte, so just another thing to remind everyone. So just remember that the software does automatically calculate and design a lens's toricity based on analysis of the elevation between the two principal meridians. And if that delta sag is greater than 30 microns, which is here, you will then it will then automatically design a toric. Hand it over to you, Shah.
All right, so what we've done here is just a basic ortho-K design. Jagger put in there -5, -1.25 diopters of astigmatism. And off the bat, the first thing we want to do is just look at the bottom right section of the display page. And what we're looking for is the balance of the bearing zones. That's the blue areas under the alignment curve. And off the bat, we can see that both the horizontal alignment curves are showing those blue patches. And remember, those blue patches is your area of most bearing on the cornea. It's neither good or bad. It's just showing you that the lens has even bearing over the horizontal meridian. And we'll talk a bit more on this as we move into Bespoke. But for any corneal lens, it's important that the weight bearing is over the horizontal meridian. It stops the lens from lateral movement, but it does allow that slight up and down movement with the blank. The next step that we will then look at is the edge lift. In this case, we're aiming for about an 80 to 100 microns of edge lift. Now, by default, the lens design is large. It's 0.2 millimeters smaller than the HVID. And because we're fitting right up to the limbal area, it is important that we have sufficient edge lift, allowing the lens not to ride onto the vertical limbal area. So Jagger is just checking that for us. Jagger, do you need to up the edge radius there for us a little bit?
Yeah, so this is actually quite a classic one that we can check for. Ideally, because we're making these lenses a little bit larger than we're used to now with the latest version of the software. As you can see, the HVID is 11.2, and one of the latest updates is we've changed the lens design so that it calculates the diameter to be 0.2 off the HVID. We want to make sure if we're making a lens that large to have enough edge lift. So this edge is probably around 65, 70 microns. I want to make sure on the horizontal meridian, which is where this edge lift here is on the top, I want to make sure that's at least 80. So let's try and change our edge radius here. And the edge radius controls this curve and obviously the amount of edge lift. So if we go from 9.8 to a 10, click apply, we'll see that increases there.
So a question we had in the past is, when do you use the apply button and when will you use the optimize alignment curve and Z-zone button? So when you make any changes, especially on the advanced parameters, it is changing the relationship between the lens and the cornea. And so it would mean that the central tear film thickness, for instance, would not be optimal. So you have an option of where you can manually go in and moderate or change the Z-zone and the alignment curve values, or you can ask the software just to automatically redesign the lens to allow an optimal relationship between the cornea and the lens. So anytime that you want to apply a change to the lens but do not want the software to optimize it, you will use the apply button. Otherwise, it's always best just to use the optimize button. So in this case, Jagroot has increased the edge lift radius, he's flattened it. Because it's not really changing the rest of the relationship, in this case, we can either use apply or optimize.
Absolutely. And so what I've done here also, and this is what I do sometimes when I've got quite a difference in the edge lift between meridians, is I'll draw out a box and I'll and then I can get more in-depth information. Anytime I click on the simulation, it's going to produce a cross section in the top box wherever my cross is, my blue cross is here. It's going straight through the lens simulation. Then it will take 90 degrees away, and it tells you those degrees here. So that's just for everyone's reference as to why that's done in the way it has. Anytime I go into here and reload the map, it'll automatically start the map design at the principal meridian, so flat and steep meridian. Okay, so Charlotte, are there any other comments for this brief summary on the iSpace AutoK design?
No, I think we've done it in week 1 or 2. So what I'd like to do now is concentrate on some of the other products we have, which is the Bespoke alignment lens. Now, not too many people are familiar with this lens, so we would like to go through the process of designing it. So you'll see it works exactly the same as designing a forged lens, except that we choose the Bespoke product, and the measurement remains the same, and you enter the refraction in the same way. Just a key point here when entering refraction, because we're dealing with normal GP lenses, is the vertex distance is now more important. So if you're dealing with high powers, let's say you're dealing with -12, it is important to manually measure the vertex distance, as this can have quite an impact on the final back vertex power of the lens. So in this case, Jagroot's adding -12, -125, 180, and he's going to leave the vertex distance at 12 millimeters. So the design process is the same. We click done, and hopefully his computer is sped up a little bit. I'm not sure what is running in the background, but obviously iSpace is dependent on the processor of your computer. So the bigger the processor and the more the memory, obviously the quicker the calculations is going to be. So Bespoke lens is a day wear lens. This is a normal GP lens. And if you look at the lens construction, it's made up of 3 zones. We've got our central back optic zone, that's a sphere. We've got a secondary zone, which we also call the alignment curve, and then we have the edge lift. Now, the fitting philosophy of this lens is similar to AutoK lenses in the sense that the weight distribution, the bearing, does not happen in the back optic zone area, but rather on the alignment curve area. So the fitting philosophy is quite similar to designing and fitting a forged AutoK lens. Now, the beauty of this lens, because we're placing the weight distribution into the alignment curve, it means we can design the lens larger but still keep the optic zone reasonably small. The problem with going with large optic zones on GP lenses is there's a higher risk of the lens suctioning onto the cornea or adhering to the cornea. So by keeping the optic zone at a basic 7 millimeters, we can enlarge the lens to fit a bigger percentage of the cornea, and that difference in size is taken up by the alignment curve. So because we're fitting the weight, the bearing, into the alignment curve to the periphery, we're spreading all the way to the periphery and not applying weight or pressure on the center of the cornea. And therefore, the lens can be larger and we don't get that adherence forces that we typically get with these big optic zones. So the advantage of the larger lens is that it stabilizes better, it tucks better underneath the top and bottom lid, but specifically the top lid, and so there's a bit of improvement in comfort. So what Jagroot's showing here is the default lens that iSpace designed. So again, if you look at the top box of the cross section there, you can see the slightly central back optic zone radius sitting there with a slight tear film thickness of 2 microns in the general area. The blue then again represents that alignment curve. And what we're looking for here again is that weight distribution, the bearing, those blue patches sitting over the horizontal meridian, distributed underneath the alignment curve. And we want a bit of space in the vertical to allow for that 1 or 2 millimeters of movement with the blink. So Jagrid, anything else that you want to add at this point?
Well, Charles, just actually a question. When you're designing bespoke and it's a daily rigid lens, and just like we all have rigid lens practices, we all do things maybe slightly a bit different. How concerned are you with this design about the edge lift and the vertical and horizontal meridian, like we get questions about ortho-K? Do you have any kind of comments around that on your philosophy or fitting style?
Yeah, obviously with any GP lens, it's important to get the edge lift within a certain parameter, a certain value range. If it is too narrow, obviously the lens doesn't get enough tear flow underneath and it can adhere and you can get staining. If it's too excessive, you might find the patient uncomfortable more so with the lens. So with the bespoke lens, a good range to aim for is right about the 60 to 80 microns of edge lift. Now this is less than what we do with the ortho-K lens, but we find with that 60 range, it's still sufficient to get enough tear flow underneath the lens. And the reason for this is because eye space can align the lens so well with the cornea, you get this very smooth, well aligned lens running over the whole surface of the cornea. You only need a bit of an edge lift to get tears underneath and the lens will lift up and flow comfortably, which further enhances the comfort of the lens. So my suggestion always is aim for about 60 to 80 microns over the horizontal meridian. So in this case, we're quite close to it. I'm guessing that looks to be about 50 microns. So the same with ortho-K, we'll go to the edge and we'll just flatten that edge radius by a small amount and click apply. And we should see that edge go a little bit more, reaching that 60 micron point that we're aiming for. So Jagrid, the center part, the central tear film thickness, where would you aim that to be?
So this is actually probably depends on our fitting philosophy. I tend to fit a little bit, my rigid lenses or daily rigid lenses a little bit flatter than most. That 3-point touch or that feather touch type appearance. So when you have a look on underneath a fluorescent simulation, you'll have minimal fluorescent there. And obviously, as we know, with if a lens has less than 20 microns of fluorescent underneath, it will not illuminate. So it may appear as if there's touch when really there isn't. That's kind of one of the times when I also have been really grateful to have access to things like an OCT to make sure that I definitely have clearance, especially with some of my proud cones for keratoconus and all very high astigmates. So yeah, I just wanted to, that's how I personally fit. So in this case, where how it's 2 microns, I'd probably prefer it to be maybe closer to 10. But that's just my personal preference there. So if I were to modify things, I'll be modifying a back optic zone radius, because that's going to steepen that back optic zone there, which is going to give us a little bit more clearance. So it started off at 7.8 by the natural toric calculation of the software. So I would start at 7.55, and let's just re-optimize this lens and see how that turns out. Excellent. So now we've got between near 8 to 10 microns. That's where I like to fit closer to 10. Other practitioners that I've seen prefer to fit nearer to 20 microns or more. Just bear in mind that that can also create some, I suppose, lens adhesion or lens suction, and could create some forces or changes there. Typically in the old days, we used to call it a spectacle blur, where you'd have the unintentional molding of an improperly fit rigid lens. We don't really see that so much now with virtual fitting. because of the lathe technology, and also the lens designs now are coming out significantly better. Charles, do you have any other kind of comments to add to that?
Yeah, so I think a good aim for the bespoke lens is that your central tear film thickness should be somewhere not touching, so let's call it 1 microns up to about 10 microns. Within that range, you should be fine. As long as the weight distribution or the bearing is sitting over the alignment curve and not touching in the center, we are good to go. Rightfully, if the central tear film becomes too much, you're going to see some molding effect happening. You're going to see a bit of steepening in the center, and the vision might deteriorate just a small amount on every blink. So the closer we can get that back optic zone to the cornea, obviously the better the optical effect will be for the patient looking through it. So if we look at the basic design parameters on iSpace, so for those of you who've been following us with Author K, let's just recap. The delta K is 1.46 diopters, but more importantly for us to decide if we should fit a rotationary symmetric lens or if we're going to fit a toric design, is the delta sag over the 9mm chord, the elevation difference. So in this case, our elevation difference is 56 microns, and this decision criteria is more than 30 microns. The software will switch over to a toric design, which it did in this case. So if we look at the design parameters, the flat meridian has a 7.75mm back optic zone radius. The alignment curve is 7.15mm, but that's linked to an eccentricity value as well. So if Jagrid can go to the bottom advanced parameters, you'll see the alignment curve eccentricity by default is 1. You can change that. So certain corneas, you might find that the alignment curve has got too much of a U shape, or in other cases, you might find that you don't have that U shape, it's too straight or it's pinching, and you can then increase the alignment curve eccentricity. That's particularly helpful as you start moving towards unsymmetrical corneas or early keratoconic type of corneas, where the eccentricity tends to increase. By default, we find for most normal corneas, the 1 alignment curve eccentricity is more than sufficient to get that alignment curve to fit properly. You've got your diameter, 10.4. You'll see it is smaller in diameter than what will fit the Forge Author K lens, but that typically is still a large, or seen as a large diameter lens compared to some other GP designs out there. As with iSpace, all the parameters is modifiable. So if we look at the back optic zone diameter, currently it's 7. If you feel that you want to go a bit smaller or larger, you can change that value and the software will redesign it. So if we look at the back optic zone diameter, it's 7. Let's decide we rather prefer that to be a 6.8. All that Jagrid needs to do is go down to that block where it says BOZD and then change the number from 7 to 6.8. He clicks optimize, and the software will then redesign that same lens using a 6.8 optic zone. And so you can play around with the various sizes as you wish. If you want to change the alignment curve eccentricity, the same applies. You can just change that value, let's say to 1.2. And again, we just click optimize. It will then redesign the lens based on those parameters. And you can see we're getting a little bit more of a U shape. It's lifted the alignment, the central tear film thickness by a micron or 2. And so you can play around with these different variables, but we found for most cases, just sticking to these standard parameters should be more than sufficient to get a good fit on the eye itself. So in this case, yeah, Jagrid?
Well, and now, Charles, just wanted to get your opinion. So who is the most ideal candidate for, say, a bespoke fit? I mean, I use it a lot on my high regular and asymmetric astigmats, but still within the parameters of what we'd call a normal cornea,
Yeah.
quite a lot. Would you agree? Like, I mean, yeah, like in New Zealand, we obviously have a health board subsidy. So our national government has a health board, and so if you are over a certain prescription or have a particular corneal condition, they will subsidise the cost of these types of specialty lenses for the patient. Because glasses simply aren't the most appropriate form of correction. That also includes anisotropes and anisotonics, as well as high ametropia. But who are you fitting this with, or would normally be fitting this with in a textbook case, the best cases?
Yeah, I mean, I think you've touched on that. It's a normal day wear lens, meaning you can fit anybody with a normal cornea, but we find people will use this quite often when they're dealing with high prescriptions or they're dealing with high astigmatism and slightly irregular corneas as well. You can modify the lens for basic keratoconus fitting, but you have to do that in association with a known fitting set. The moment we're dealing with irregular corneas, the spectacle prescription becomes unreliable, and therefore you have to have some form of diagnostic fitting lens on the eye to get certain fit parameters, which you can then feed into EyeSpace, and the software will from that point onwards calculate the final optics of the lens. So let's look at another example here. So this is a much higher astigmatic case. That looks to be 5.79 diopters of corneal astigmatism. So this for me would be an ideal case for the bespoke lens. And I want to show you how quickly it is to design a bi-toric lens. In the past, it took a bit of calculation and a bit of fitting skill to get a bi-toric fitted. And so my experience with EyeSpace is these are one of the easiest cases to do with EyeSpace, providing you're getting a good map. And so this becomes almost an easier fit to do than even a soft lens. And the beauty of the system is you can play around with the virtual design. In your head, you can try different base curves, you can try different optic zone sizes until you get the fit optimized without fitting a single lens on the patient's eye. So from the patient's experience, they come in, you have a discussion, you decide to do a GP lens, you do a couple of corneal maps, you do your spectacle prescription plus the other peripherals that you're going to do with the eye test, and you send your patient home. Next time they come back to you, you already have a finished product. So by the time you put the lens on the eye, it's already optimized for the eye shape and the optics are already in place. So the first introduction of your patient to a GP lens is a fully functional and well-aligned lens. So the comfort levels is again a lot better and the vision's instantly there. So the first experience is much, much better than trying to fit a number of diagnostic lenses onto the eye. You put an anesthetic in, it's in, out, in, out. So the patient expectation lowers on that first day of fitting. So we find this to be a really nice tool for doing those high toric cases. So in this case, Jagrud's added there -5, -6.5 diopters of cylinder in his spectacle prescription, horizontal axis, and he modified his vertex distance to 11. And I can't stress how important that vertex distance is. If you get that number wrong, the back vertex power is going to be out when you deal with these high powers, and the patient's not going to see comfortably, obviously. So in this case, it's produced a lens that we do need to make certain changes to. So again, my eye is going to that bottom right section, and I'm looking for the central or the bearing area underneath the alignment curve. In this case, the blue is sitting there towards the 11 o'clock position, and so therefore we require to tilt the lens to allow the balance to shift over to the horizontal meridian. So Jagrud's going to click on tilt and position. That brings up our tilting screen, and he's going to click in the opposite direction of where the blue is, and the software will re-simulate the lens, so allowing the tilt at the bottom to come a little bit closer to the cornea. So in this case, the blue is shifted to the left, and so we're going to click on the opposite right to balance the lens weight distribution more to the right. And this is a process we'll continue with until we get balance. So either what we are looking for is the blue should sit over the alignment curve, equally distributed between left or right, or we get this tripod or triangle appearance where we've got 3 points of contact and we can imagine the lens not being able to tilt or move in any further direction because of that stabilization. So now we can go back to the simulation. So Jacob, would you leave it at that point or would you go a little bit flatter on the back optic zone radius?
Yeah, so that's a really good question. I'm actually happy to, at my first initial lens, go a little bit flatter just from the experience I have in the software and how I personally like to fit. I've got other colleagues in my practice who are very happy to leave the lens, this lens as it is. And so that's why I talk about your fitting philosophy, what you grew up with. And even within practices, you can have differing opinion. The big thing for me is making sure that there's no binding and there's still really good comfort. So in general, I tend to get the lens as close as I can to the cornea without insult.
Yeah, in reality, the virtual fitting does allow us to become quite critical on the central tear film thickness. So if we do lower that central tear thickness by, let's say, 5 microns, it will, in my opinion, be a little bit better to go a little bit closer to the cornea. But in reality, when you place a lens with a 15 micron central tear film thickness on the eye, compare same lens with a 10 microns of tear film thickness on fluorescein evaluation, you will most likely not see any difference to the fit. But because the virtual fitting allows us to be more critical, we can make these minor adjustments, which in the end is going to be probably a 0.05 difference in the back optic zone radius. So what Jagrid's done there is he's flattened the back optic zone radius of the flat meridian. So what we need to do now is go back to tilt and position because we've altered the fit relationship and just retilt the lens to allow that equal distribution to occur again. So he's tilted it and we can see we've now dropped that central tear film thickness by about 5 microns by flattening the back optic zone radius of the flat meridian from 825 to 8.3 millimeters. So at this point, I'm happier with the central tear film thickness. I like it to sit between 1 and 10 microns, so that 11 is fine. So the next step is to look at the edge radius. So again, we're aiming for about 60 to 80 microns of edge lift. So a way to zoom in is to click with the left mouse button, draw a box, and then it will enlarge that specific area, and we can see we within that 60 to 80 microns of clearance. So at this point, the lens design looks good. Now, depending on your fit philosophy, you can leave the back optic zone at 7. If you want it a bit smaller, you can go to 6.8, or you can enlarge it to 7.2. In reality, it's not going to make too much of a difference, and you'll probably only pay attention to that if you have a slightly bigger pupil size and you want that optic zone to be a bit larger. But again, because the lens is so large and well aligned, you will find that the lens stabilizes quite well on the eye. So there's not too much movement except for that bit of up and down movement.
Very cool.
Yeah, so that's a really good point there, Charles. If I had a pupil of this size, I would just leave it at default settings. If I had a younger patient who had quite a large pupil, and you know, let's say they were indicated for a
thank you.
Can we just mute someone's microphone there? I'm not sure who that is. If we can, you know, if we have a patient, let's say I've got a high hyperope, and they happen to have a larger pupil than this, then I may look at maybe potentially even increasing the back optic zone diameter, or leaving it the same, because we know that we're going to get less halos and or glare or issues like that. But I always check the pupil size before I'm fitting anyway. And that may be in my topography software, may not necessarily be in within our software. So from here, the next step, unless there are any objections there, Charles, or anything else that we've missed, is we probably want to add this to the shopping cart.
Yeah, I just want to quickly highlight perhaps one more thing, Jagrit.
Yeah, sure.
If we look at the overall design, again, the flat meridian relates to where those two engraving lines are on the lens, on the simulation. Keep in mind that that flat meridian can rotate to any position on the cornea depending on where your axis is of the corneal astigmatism. So it won't necessarily sit at 0 or 180. It can sit at any point across that cornea. So keep in mind the flat meridian values on the design page always correlate to where those two line engravings are on the simulation. So what iSpace did by default, the only thing we really did is we've tilted the lens to allow for a better simulation of the lens on the cornea. We flattened the back optic zone by 0.05 millimeters, which is not much, and we most likely could have left it where it was. So iSpace designed a back toric lens. So you can see the back optic zone radius is 8.3 by 7.4 millimeters. The alignment curve is separate values, meaning it's a toric periphery by definition, and it's determined the overall size based on the measured HVID. So by design, we have a fully functional back toric. Now, if you're dealing with back torics, you'll know doing the calculation for the back vertex power can be cumbersome. iSpace has streamlined that process for you as well. So if you click Add to Cart, what you'll see is the software analyzed the data and it determined the most optimal back vertex power for that lens. Now, there is a tick box there that says supply as a spherical power effect or a compensated bitoric. So ideally, when we design a lens, we want that box ticked. The reason for that is the back vertex power will then neutralize the tear power, and therefore the lens will act like a spherical lens on the eye. So if the back toric lens rotates off axis, it will still function on an optical level like a spherical lens. We won't reduce any residual astigmatism. But in certain cases, because of lenticular astigmatism, the software then decides it cannot use a compensated bitoric. It needs to add extra cylinder in the front surface of the lens, and then therefore that tick box will be unticked. So the software by default will make that decision for us and decide which is the most optimal way to design or calculate back vertex power. If that tick box is unticked, it means it's adding extra cylinder, but it also means the lens now must be positioned in the way the simulation tells us it's going to rotate on the eye. So if you look at the lens on the eye, those two lens engravings should sit in more or less the same axis position as what the simulation shows. If the lens rotates off axis relative to where the simulation is, we're going to induce cylinder by that lens rotating off the eye. So even with the back compensated bitoric tick box unticked, there is residual astigmatism in this case, and you'll see there's minus 1.5 diopters sitting at an oblique axis. When you get this, it means that there's some lenticular astigmatism in the eye that we cannot correct with a GP lens. And this is typically if the spectacle axis and power is quite different by more than 20 degrees to what the corneal axis is. So that's just a very good dashboard on the car to warn you that certain things might go wrong if you're not careful. So I'm just looking at some of the questions coming through at this point. Is it a set of percentage of HVID? Yes, the lens design is based as a percentage of the HVID. So as the cornea goes larger, the lens as a percentage will go larger as well. So back to the spherical power effect, just watch out for that residual astigmatism. If it is like it's now, I'd be a little bit wary going forth and ordering this lens, and I'd rather revisit my map and make sure I've done the best map capture than I possibly could have. So if we're happy with what we've done now, the next step would be to go to add to cart, and we will then go ahead and order the lens. So if we can go back to the corneal astigmatism here, we see that the flat axis is at 172 degrees. We've got that 5.79 diopters. There's a 6.5 diopters there at an axis of 180. So there's a bit of a misalignment sitting there in the astigmatism, and that's probably why that is why we're getting that slight residual astigmatism coming through. So
yeah,
what do you have?
And so the higher the sill, so the higher the cylinder, and the higher the cylinder means that you're going to have less give or less laxity in your system in terms of when we do the calculation for residual cylinder. So if your cylinder is set at 180 degrees, but you've got 172 degrees where the actual corneal sill is, then that's going to magnify the effect as the cylindrical power goes up in terms of the error. So then you're going to get misalignment. This wouldn't matter so much if it was a lower degree of cylinder. So I always put this case in here so that people actually look at the residual, so that then when they get the lens, put it on eye, they understand that, hey, I was expecting to have a residual cylinder here in a case like this. You know, that's probably the main take home here, is just making sure we understand what the residual prescription is in eye space, what it means, and then if everything's there, it should all make sense. So if you were to trial frame and put that residual over the top, the vision should improve. Now, obviously, we have a residual tolerance because it doesn't have to be exactly perfect in a case like this. As long as we have a reasonably good vision resulting in it, will mean that this is a lens that we can continue with. Admittedly, yes, this is an example where we've got 8 degrees of difference between the spectacle prescription and the flat k-axis, but I think it's a good example to show how that residual can develop and how we don't necessarily have to have, how we may not necessarily have 20/20 or 20/15 vision in cases that do come across that are a bit more curly like this one.
So let's take another example where the optics will work comfortably. So if we can go back to our patient base, when you open up iSpace for the first time, it's filled with these demo cases. So in this case, we're going to take the demo toric, which is the bottom one there. And this design, or this cornea, has about a 3.5 diopters of corneal astigmatism. So let's design another bespoke lens. So we're going to go to new lens, choose the bespoke. Again, we just measure the HVID. And you can see it's now becoming quite an easy process once you've done this a couple of times. And let's take an interesting prescription like -12, -350 at axis 10. And we'll design the lens. So again, once the software has finished calculating the lens parameters, the first thing we should do is our eye should move towards the bottom right section, and we want to look at the lens simulation. And the first thing we want to pay attention to are those blue patches. In other words, has the lens tilted in such a manner that we've got equal weight distribution. So in this case, we can see the weight distribution is more over the vertical meridian, which is not ideal. So the easiest to fix this is just to flatten the steep meridian. So where it says 7.6 on the steep meridian, we're going to flatten that by 0.5 or 0.1. So Jaggered, if you want to put in there 7.65, we click apply. And so what we should be seeing now is the weight distribution slowly moving towards the horizontal. So in this case, I'll flatten the steep meridian by 0.5 more. So we'll make that 7.7. Click apply. And so as we're lifting the vertical optic zone away, the weight distribution reshifts back to the horizontal. So this is somewhere I'm comfortable with the central tear film thickness. If you're a bit uncomfortable with that, you can increase the back optic zone radius by 0.05. But at this point, I'm happy to leave it at that level. And so the next step is we want to check the optics. So in this case, our corneal astigmatism and the axis of the corneal astigmatism correlates more. So if we click add to cart, the software will analyze and then calculate a back vertex power for us. So in this case, we've nailed it. There should be 0 residual astigmatism coming from this first. So again, if we look at that supply and spherical power effect, Jagrid, if you want to click on that for us, notice that the cylinder then changes to -3. Now keep in mind, if it is a compensated bitoric, it means the lens can rotate off axis and the optics will act like it's spherical. You won't induce any cylinder. But if we leave it as a compensated bitoric, the astigmatism is -1 diopters residual. So the software will automatically switch over to a non-compensated bitoric if that corneal astigmatism is more than 1. And so that's why the box was unticked. So again, Jagger, if you want to untick it, it changes the cylinder, the back vertex cylinder, and by doing so, we can reduce the corneal astigmatism to 0. So that's typically something that you won't have to do yourself. I just wanted to demonstrate why the software will automatically switch between those two options. So this is the easiest way, as you can see, how to do a bitoric lens. It didn't take too much effort to do it. All you needed to do was make sure the tilt is correct, the back optic zone radius is optimized. You click the optimize button towards the end, and once you're happy with the simulation, you add it to cart. The software calculates the back vertex power. If your residual astigmatism is within acceptable means, you will then go ahead and order that lens. And so you can see the ease and simplicity of doing bitoric lenses, for instance, over what you might have been doing in the past with trial fitting and manual calculations. So it really makes fitting GP lenses a pleasure. Just like Ortho-K, it's simplifying the process, but we still end up with quite a complex lens. And this lens, when fitted, should be optimized to the corneal shape, and your optics should be optimal for that patient when they pop the lens in the eye. So a practical example I had in practice, I had a small boy that was referred to us coming from the more rural areas with a very high prescription. He was in the -16s and he was only 12 years of age. They tried to fit soft lenses. Obviously, it's beyond the range of Ortho-K. So the patient flew down at their expense to our practice. We did topography maps, did the prescription, did everything else, and then sent the patient home. Because of just South Africa and the environment, we had to bring these lenses in from overseas. So there was about a 10-day delay from order to receiving the lenses, and the parent flew the child back. Now, keep in mind, for them, it's an hour-and-a-half drive to their closest airport. It's an hour-and-a-half flight to us, plus another 45 minutes of driving from the airport to the practice. So the poor parent had great expense bringing the child in every time coming to us. So I was very nervous and worried and tried to make sure that the lens that I put on the first time was the best that I could do to try and minimize the time in the chair and the expense of the parents flying in. So that's the confidence I had in iSpace. I literally took good maps, spent most of my time getting a decent map, did the prescription, designed the bespoke lens, ordered it in, and the first time the patient came in, we popped those lenses in, and lo and behold, they worked, and they worked well. And it's now 6 years later, 2 pairs down, the patient's still wearing their RGP lenses. So it does allow us to do very complex fits with minimal chair time and still easy to do, because even when your patient's away, you've got their corneal maps, you've got their digitized cornea, and you can sit and play around with different designs like you would do with trial fitting a real diagnostic lens, ending up with a product that you're happy with, and then order and have the confidence when you receive it that that lens will be as good as it can be, just based on virtual fitting.
We thought we'd now just open up the, as we're coming to the end of today's lockdown lecture, we just wanted to basically keep these sessions pretty short and sweet. We do appreciate you all attending. Does anyone have any kind of questions around the iSpace Bespoke product from this introduction for Charles or I? Oh, we've got one from Alex there, Charles. So welcome, Alex. What time is it in Russia there? It must be about 7 a.m. I suppose. He says, how about a front toric? What kind of stabilization can be used?
Look, you can add, it's always ideal when you do a front surface cylinder to have a back toric. A back toric definitely stabilizes the lens a lot better, meaning that there's a difference in the optic zone radius between the steep and the flat meridians. You can do spherical base with a front surface cylinder, and then we'll have to add a prism for you in the lens to stabilize it. But now there's many factors playing a role here. So if your front surface cylinder is horizontal or vertical, the prism will do a much better job in stabilizing it. Whereas if the front surface cylinder sits in an oblique fashion and it's quite a high cylinder, we might even struggle with the prism stabilizing the lens. But if you fit a back toric, you can fit any front surface cylinder on there, and generally the lens will do a good job in stabilizing.
There's another question there about the Zeiss Eye Profiler and its Atlas software, and does iSpace work with that? Well, the answer is pretty simple. It will work with most topographers, and the way that we use it when, say for example, we've reached out to Zeiss and Atlas, and we're still waiting to hear back from them because we've had users requesting this functionality. We can actually create a reference map using their data, and then we can design off that. And as you'll see what Darren's saying, many of our doctors use the software to help their new associate docs who have limited GP fitting knowledge, and they also use that product, the Zeiss Profiler, as well. Yeah.
Jagger, this might be a good time maybe just to run through a demo of doing a reference map and just showing how easy it is. So if you don't have the patient on iSpace, you can manually create a new patient. So if you click on menu on the right-hand side, you can see there's an option there to generate a new patient. And if you click on new patient, you literally just have to put in the name, the surname, and the date of birth. And that's the way that you'll generate a patient on your system. You will click OK. And now if you click on that patient on the right eye, obviously, because you have not imported any maps from Medmont or Oculus, you'll have to now create that reference map. So we go to manually enter corneal data. Click on it. You decide if you want to do the right or left eye. You will either decide to put radius of curvature values in, or SimK or delta K values in the opters, and you would physically just fill in the numbers. And if your software provides the eccentricity, the average eccentricity of the flat and steep meridian, you will enter those values and the overall diameter of the lens. Click OK. And so if you go to left eye, you will do exactly the same. And then you have your reference map. So this is basically a mathematical map generated from the input data. And now this gives you a platform to design lenses on. So the same way as you would design any other lens, you will click on Forge or Bespoke. You will put the HVID measurement in, you will put your prescription in, and the software will design that lens based off the input data that you've just created. So that's an easy way to take any other topography data that you have, put it into iSpace, and then you can design the lens based off that corneal data. And from there, you can optimize the fit again. So in this case, you will probably want to reduce the back optic zone radius value. you'll change that value perhaps to 8.10, and then the lens alignment should look a little bit better. So you can do exactly the same with Author K as well. So if you go to New Lens, you click on the Forge option, and you go ahead and enter that description. And then the software will then design an Author K lens based on the corneal data that you have. And we do have a number of practitioners who use this system of reference mapping using topographers that's not capable of importing into iSpace, and they still generate Author K lenses from that, which they then fit. Keep in mind, you do lose a bit of the detail from using an actual map versus the reference mapping. So, but for normal Author K cases within the normal range of planar up to -4 with reasonable astigmatism and nothing strange to the cornea, the system will offer you an alternative that works just as well. So the reference mapping is another option if your corneal topographer is not capable of importing into iSpace directly.
Excellent. So I'd probably just hand over to Darren and Angela for any other final kind of comments or queries. But thank you all for attending today's session from Charles and I, and we look forward to the remaining sessions that we have during our lockdown lecture series. Darren, Angela, do you have any other comments or queries around the product?
Yeah, I just wanted to thank Jagger and Charles for joining us today and sharing this information. If any of you have specific topics that you would like them to cover for our next lockdown lecture, which will be a week from today, please email Angela, or if you have any other questions, and you can email her at ispace@customcraftlens.com, or if you want to type your name in the comments section, then she can get your information from there and reach out to you. I appreciate everybody taking time out of your day, and Angela, you have anything you'd like to add?
That's exactly what I was going to say, Darren. And if you'd like to send a picture of yourself during the presentation, as I said, we're going to feature some of our attendees on our iSpace page. So send them along, and it'll be a great opportunity to promote your practice. And thanks for attending again.
Thanks, everyone.